Welcome everybody to the start of Algebra 2. And before we dive into our textbook really kind of expects you to remember a lot of things from Algebra 1 and even geometry class a little bit. So we like to take a little time, we call it our Chapter 0, before we get into our own textbook. Just take some time to go over some of the things from Algebra 1, review some concepts that are going to help make an easy transition into our textbook. So here's day 1 of that Chapter 0. It's on graphing lines and evaluating functions. Really good way to kick off the year. Let's get started. So first of all, when we're going to graph a line, we want to concern ourselves with the slope of the line. That's a really nice, indicative, descriptive term that's going to tell us an awful lot about the line and what it means as it moves through the coordinate plane. A rate of change is just a ratio. Usually we see it as a fraction that shows how one variable changes when compared with another. When we're talking about lines graphed on a plane, we're talking about the change in y, the output of the function, the height of the graph, over the change in x. We often call this the rise over run. This is probably how you saw it in Algebra 1. But the rise, since the y values on a graph measure the height, the change in y is some change in height, some rising or falling. The change in x, well, the x-axis moves left and right, so the run is going to be the change in x. Is it moving to the left, moving to the right? That type of kind of movement. To find the slope of a line, we're just going to look at the change in x, change in y. So if I have 2 points, x1, y1, just meaning the x coordinate of my first point, y coordinate of my first point, and similarly x2, y2, the slope, notice that we use the variable m for slope. It's the slopiest letter we could find, slopes up and down. We have the change in y, y2 minus y1, over the change in x, x2 minus x1. So we can go ahead and if we have those numbers, plug them in and simplify, and boom, we have our slope. Some things to remember about slope just generally is that a positive slope will rise from left to right across the graph, and depending on how big that number is, so if I have a fraction that's pretty small, pretty close to 0, like 1/2 or like 3/15 or something like that, it's going to be a very shallow rising line. It's going to be very, very gradual like this. Where if I have a slope that's like, I don't know, 8/3 or something that is a number that's bigger than 1 or really, really big for that matter, it's going to be a very steeply increasing line. So for instance, this could be a slope of +1, this could be a slope of +1/2, and this could be a slope of like +4. Just so we know, as the slope becomes a bigger positive number, the line gets steeper as it rises to the right. And that's just a nice pattern that will help us visualize our graph before we even put it on the paper. Similarly, if we have a negative slope, and we go to graph that line, let's say our slope is -1, then our line will fall from left to right. It will decrease as we read that from left to right. If I have a bigger negative number, it's going to be a very steeply falling graph, so this could be like a -3 slope. And if I have a small negative number, like a -1/4 or something like that, it's going to very gradually fall to the right. So those are just some examples of what we could expect our graphs to look like just by knowing what that slope, that rate of change, looks like. Those patterns are very, very helpful. All right, so our first task is to actually take some data and figure out what the slope is going to be. So for our first example, we have 2 points, and just because I want to take thorough notes here, I'm going to go ahead and indicate what my x1 and y1, my x2 and y2 are.
Salpine to the visitor's desk, please. Andrew Salpine to the visitor's desk.
I apologize for the interruption there if those beeps got in the way. But to calculate my slope, let's go ahead and plug in those numbers. My ending y is a 10 minus my starting y is a -5. And I know you can probably do some of this in your head, but let's write it out in the notes. We don't want to fall victim to silly negative sign mistakes. If we can correct this early in the year, start thinking through clearly, it's going to help us out in the long run. x2 minus x1 is a -7 minus -2. And now let's go ahead and clean that up. 10 minus a negative 5. Now I can clearly see I'm taking away a negative. I know that's 10 plus 5, 15. In the denominator, negative 7. I'm taking away negative 2. That leaves me with negative 5. It's like adding a 2 to it. So final answer, when I simplify that, I get negative 3 for that first slope. So if I were to graph that, I would expect to see a pretty steeply plotted line that's falling to the right. Example 2, here we've got a line that's already been graphed for us, and we want to determine the rate of change, determine that graph's slope. So I can see that it looks like it's pretty gradually rising to the right. So I'm expecting a small positive number to represent this slope. And that's just kind of what I'm thinking just by looking at the graph. So when I get an answer, I can see if that answer makes sense. Well, based on the graph, you can see that the way that they've labeled this grid, they're counting by twos, and they're only labeling every other line. So I want to be sure that I'm reading this graph very carefully. Sometimes when you see graphs, the y-axis will go by hundreds and the x-axis will go by ones or twos or something like that. So we want to be sure that we're understanding where this graph is going. And I'm just going to scan that graph from left to right and look for 2 points. I want to turn this into a problem just like the one up above, 2 points where I can actually find numbers where that graph cleanly crosses the grid. One of those points, it appears to be right here. That's where my graph ends up, it looks like, if I'm reading it left to right. That's the point 8,4. And if I scan, I might be tempted to choose this point right here, but if I look closely, I can see that graph is underneath the grid there. I don't think I can trust that point. Maybe there's another accurate one. So I'm going to keep scanning that. And then right here, I find another point that looks pretty clearly to be a place where my line crosses the grid very cleanly. That's the point -8, -2. Again, making sure that I'm following the labels very carefully. And now that I have those 2 points where my graph cleanly crosses the grid, I can set this up using my y2 minus y1, 4 minus -2, over x2 minus x1, 8 minus -8. And let's simplify that. I get positive 6 over positive 16, which is 3 over 8. And I'm just going to compare that before I move on to anything else. I'm going to compare that to what I had kind of, I don't know, estimated would happen at the start of the problem. I said I would have a small positive slope, and when I ran through the numbers, sure enough, I ended up with a pretty small number. It's less than 1, it's pretty shallow, and it's a positive one, so it's rising to the right. That answer agrees with the graph. I can feel pretty confident about that. All right, for the next example, now we're going to take that idea of slope and we're going to attach that into the creation of a graph. So we're going to talk more about like the equations of lines in the next lesson, but this one here, we have what is called slope-intercept form of a line, where it's solved for y, and then y equals mx plus b. I'm sure you remember that from Algebra 1. I certainly hope so. But now if I look at where the numbers are occurring, I know that that -3/2 is the slope. And so that is my rate of change. And now, before I even start to plot points and put this on the actual grid, I can have an understanding that, hey, this is a number that's bigger than 1, and it's negative, so I can expect that graph to go down to the right, to decrease, and somewhat steeply, too. It's not going to be a very shallow one. To plot this line, we're going to start with the +5, actually. That's the y-intercept. So on the y-axis, I'm going to go up to 5, and that's the first point that I know my line must contain. And from there, I can use that rise and run, that rate of change that says -3 over +2, down 3, and to the right 2, down 3, to the right 2. There's the next point on my graph. And if I just kind of eye that up before I draw the line in, does that agree with what I said the slope should show me in a graph? Decreasing somewhat steeply. And yes, it does show that. So I feel pretty confident when I draw in that line that it's matching up with the equation that I was given. All right, if we have mx plus b, that's probably the nicest way we can be given the equation of a line, because we can instantly go to the graph and start plotting points and connecting them. It's very, very fast. Here you can see a different form of the equation of a line where it's not solved for y. It doesn't look like y equals mx plus b. This is called the intercept form, or sometimes the standard form, general form of a line. And as you can see, it's just kind of laid out alphabetically, x's and then y's and then equal any constants on the right. Well, all we have to do is manipulate this a little bit algebraically and solve it for y, because, man, if it looked like mx plus b, it would sure be easy to graph. So let's take this and add the 3x. I don't want my x's on the left-hand side of that equation. Then I would have 5y equals 3x plus 7. It's starting to look like y equals mx plus b. And then to finish that off, I just need to divide both sides, and that means dividing everything by 5. Then y equals 3/5 x plus 7/5. And because it's taking that form, y equals mx plus b, that m, that slope, is right there for me. It's 3/5. That's my rate of change. And I know that when I go to graph this, I should see a line, that positive slope, telling me it's going to be rising to the right, and the fact that it's a small number means it'll be a very gradual rise, a pretty shallow increasing slope. So 7/5 is my y-intercept. That's where I'm going to start to plot this. And man, if it were 10/5, it would be 2. If it were 5/5, it would be 1. So I'm kind of falling somewhere in between the two. If we were to type it up in a calculator, I don't condone that. But if we wanted to check by getting a decimal, we'd find it's 1.4. And so that puts us right between 1 and 2 for a y-intercept. I'm going to plot that point. And then from there, I need to have a rise of 3 and a run of 5. Let's lay out that run right now. Rise of 3 would put me up about here, and then a run of 5 over here. And then just a quick eyeball check at that. Yep, it's gradually increasing. So I feel confident connecting those and calling that my graph for that linear function. All right. We're moving right along. So what we just saw were lines that had slopes, that had rates of change, but sometimes we can graph lines that maybe don't have any slope at all. They're vertical or they're horizontal. So here, I've just given a little place for us to kind of gather our thoughts on what we remember about vertical and horizontal lines, particularly with regards to slope. So a horizontal line, if you remember, that's a line moving purely left to right, no steepness to it. It has a slope of 0. And in a fraction, that would look like 0 over something. So if I'm going about my work and I end up doing 0 divided by something, I know that that's representing a horizontal line. There is no change in y, no change in height as that line moves along. For a vertical line, that's one that purely goes up and down. There is no change in the x value whatsoever. The x is fixed there. So our slope, our steepness, it is so steep, it is perfectly vertical, it is incalculable. We call that undefined. And I'm sure you remember that word from Algebra 1. When do we see an undefined slope? If we're doing work in the fraction, it's when we end up taking something divided by 0. All right, so hopefully we can use that kind of understanding of horizontal and vertical lines to help us out with graphing, the problems in example 4. So for the first one, y equals 3. That's telling me y, that measures the height in a graph, is 3. The height is always 3. So no matter where I am on the graph, it always has a height of 3. It keeps that height all the way across. So this is a horizontal line. It has a slope of 0. All right, for the next one, my x value is always going to be -7. And that is fixed. So no matter where that line goes, it has to have an x value of 7. That's a vertical line, so I know its slope is undefined. All right, this may seem a little bit backwards. If y measures height, then shouldn't that be a vertical line going up and down? No, it's kind of backwards. It means our height is fixed, so it goes perfectly across left and right. So it's kind of the opposite of what you'd expect. I do have a colleague that says the way that he teaches to his students, I really like this, says that if we have an equation that's just y equals a number, then we know that we have a line that only crosses the y-axis. And that's kind of a nice way to make that make sense, I think. If we have an equation that's only x equals a number, we know it only crosses the x-axis. That's kind of a nice way to remember that. All right, so that does it with our graphing lines review. Now it's time to look at function notation. It sounds really intense from a vocabulary standpoint, but I'm sure you've seen it before. This is an example of function notation. How you read that is f of x. And the nice thing about function notation, why we bother to have that in our number system, is we have a name for the actual output. In this case, that is the name of the function. It is function f. And we also get to see what our input variable is. So a good instance example would be, think of the area of a circle from geometry, a equals pi r squared. If I have a circle and I know its radius, that's the only input I need to find that circle's area. So I could call that a of r and treat it like a function. I input the radius and the function outputs the area. We are going to make a little annotation here. I left a lot of space in the middle because it's easy when we look at this to think that f of x is f times x. Okay, so we're going to make a little note to ourselves to call out that f of x is not f times x. Even though the parentheses make it look like multiplication, the x is telling us what the input variable is. It's part of how we're describing our output. It is not multiplication. So for letter A, here we have to evaluate this function. The function's name is f. It uses x as an input, and then what that function is telling me to do, to find my output, I take the input and square it, and then add 2 times that input as well. So now let's see, f, if I input a -3, is going to be -3 squared plus 2 times -3. I just substitute in that -3 because that's my input. All right, and now it's just a matter of cleaning up, following our order of operations on the right. You'll notice that when I input that -3, I used parentheses. I do that whenever I input something into a function. We're going to do that an awful lot this year, and man, does it make your life easier keeping track of negative signs and order of operations, what you should do next. It very much makes that clearer. So here we go. The first thing I need to do is take that -3 and square it. That makes a +9. And then 2 times -3 is -6. So f with -3 as an input produces 3 as an output. And beyond this class, whenever you see the word evaluate in the instructions, it means we're going to end up with a single number for an answer. So here we got 3 as an answer. That makes sense. They told us to evaluate. I plugged a number in. I get a number out. For letter B, here I've got some function. Its name is g. It takes a as an input variable. And here's what the rule says to do to calculate the output. You take 3 times the absolute value of 4 times the input, -4 times the input, plus 1, and then you subtract 10 at the very end. And then we're going to input a 1 into that function. Let's see what happens. G of 1 is 3 times the absolute value of negative 4 times 1. Let's use our parentheses to substitute in. Plus 1. Close up the absolute value, and then minus 10. Order of operations, we've got an absolute value that's kind of grouping our work. We better clean that up first. That 3 stays out front. Inside, I've got negative 4 plus 1. And then outside, I've got the minus 10 afterwards. Okay, I'm going to move over here just to have some more space to work with. If I finish cleaning up the absolute value, I find it's really just a negative 3 inside absolute value. And remember, when there's a number inside absolute values, if that's a negative number, the absolute value will turn that into a positive. So the absolute value of negative 3 is really just positive 3. Final answer, G of 1, 9 minus 10, negative 1. I put a number in, I got a number out, just like I should expect when I'm evaluating. And our final slide, notice the subtle change in the instructions here. Simplify the function when the input is an expression. Now I'm not inputting a number, I am inputting an expression. There will be variables left over. They did not use the word evaluate, so I'm not going to have a single number for an answer. The process, thankfully, though, is very much the same. For letter A, I've got some function f that takes x's as inputs. What that function does, it takes 2 times the absolute value of 5 times the input, and then it subtracts 1. So if I want to input x minus 3 instead of just x, the rule would become 2 times the absolute value of 5 times, not x, but x minus 3, and then minus 1. Now, because my answer is an expression, it's not going to be a number, we really don't have as much work to do on the back end of this problem. In fact, here to clean this up, the only thing I can do to simplify it any further is distribute that 5 inside the absolute value. That is my answer. The answer is going to have variables left in it because I put in something with variables. And that's kind of a nice pattern to follow. One little note about absolute values, you'll notice that and some people may be wondering, why is there still a negative inside this absolute value? If the inside of your absolute value is an expression, it's not just a negative number, then we don't change anything. So the fact that inside the absolute value was 5x minus 15, we just leave it alone. The only time an absolute value wipes out a negative is if it's just an absolute value of a negative number. Otherwise, just leave it alone, which is good. That's less work for us here. All right, and finally, here we've got some function p that uses n as an input variable, and its rule says to take that input, square it, and then add 5. So if I take function p and I input x minus 3, I take that input, x minus 3, note the parentheses, square it, and then add 5. Now, in this class, this is going to be a very early warning for you. We're going to see a lot of cases where we take a binomial expression like this x minus 3 and square it. It is very tempting to say x minus 3 squared is equal to x squared and negative 3 squared, but that is absolutely not the case. Do not fall victim to that. Remember that a square, a second power, means multiplied by itself. So p of x minus 3 is really x minus 3 times itself and then plus 5. So even though we don't see it like we expect to see it, we have to FOIL this out. And if I do the FOIL method, first times first is x squared. The outside makes negative 3x. The inside is also negative 3x. That's negative 6x total. And then last times last gives me a positive 9. And then I have my plus 5 after the FOILing. So my final answer should really be p of x minus 3 is equal to x squared minus 6x plus 14. And again, I'm not concerned that we have x's left in the answer because we had x's in our input. So that is to be expected. All right, that covers all our examples for this first day of our Algebra 1 review. I know it kind of ended with some heavier algebra, but man, if we can take the time and understand this well, it's going to make our year go by much, much more smoothly. So I hope you've enjoyed this video, and I hope it's kind of got you a little bit excited at least about our year we're going to have here in Algebra 2.